Hi, welcome back. This is a video about equality and containment. We're going to ask the question, when are two sets equal? Let's make a definition. Let A and B be two sets. We say that A and B are equal if they contain the exact same elements. If that's the case, we're going to write A is equal to B. So, let's look at an example. Let's consider A to be the set A, B, and B to be the set B, A. Is A equal to B? Well, let's write down the elements of A. The elements of A are A and B. Little a, little b. What are the elements of the set capital B? Well, they're the same. They're A and B. So remember that even though little a appears to occur twice in capital A repeated element only counts once. So the elements of these two sets are exactly the same, and therefore we would say that A is equal to B. All right, let's do another example. Here's two sets. Capital C is the set 2, 3, 1, 2, 3, and capital D is the set 4, 3, 2, 1. Is the set C equal to the set D? Well, what are the elements of capital C? Well, I see a 1, I see a 2, and I see a 3. What are the elements of capital D? Well, I see a 1, a 2, a 3, and a 4. So since 4 is in D, but 4 is not in C, then we would say that the elements are not the same, so C is not equal to D. So what we notice here is that if there is an element that's contained in one set, but not the other, then the two sets are not equal. And similar to that, if you have two sets that contain different numbers of elements, they can't possibly be equal. So those two techniques may be helpful if you're trying to show that two sets are not equal. Let's do one more example. Is the empty set equal to the set containing the empty set? Well, the empty set contains no elements. But the set containing the empty set contains one element, the empty set. So now we have two sets. One has 0 elements, one has 1 element, and that means that the sets cannot be the same. So therefore, the empty set is not equal to the set containing the empty set. All right. So another way in which two sets might be related is by containment. So what do we mean by that? Here's our definition. Let's let A and B be two sets. So we have two sets, A and B. We say that capital A is a subset of capital B if every element of A is also an element of B. And in that case, we're going to write A, this symbol, A is a subset of capital B. All right, here's another definition. We say that A is a proper subset of B if A is a subset of B and A is not equal to B. In this case, we're going to write A, this symbol B, A is a proper subset of B. So this may remind you of the relationship between less than or equal to and less than. So let's look at an example again. So we have our example from before, where we had the set C, which contained 1, 2, and 3, the set D, that contained 1, 2, 3, and 4. And so what we can see is that every element of C is an element of D. So C is a subset of D because every element of C is also an element of D. But not only that, C is a proper subset of D because C is a subset of D and C is not equal to D. That was the thing we learned before. All right, one more example here. Let's look at this chain of subsets, and indeed chain of proper subsets. So why is this true? So remember, this capital N represents natural numbers, and those are the numbers 0, 1, 2, ... And capital Z represents all integers. Now, every natural number is an integer, but we need not just that it's an integer, we need to show that they're not the same. So why are they not the same? Well, there's something that is in Z that's not in N. So, and -1 is in Z, but -1 is not in N, so they are not the same. So every natural number is an integer, and there's something in Z that's not in N. All right, so let's do the same thing with Z and Q. So remember, Z is the integers, and Q is all rational numbers. So every integer is a rational number, because let's say you had 99, you could write that as 99 divided by 1. But there are some rational numbers that are not integers. For example, 1/2. 1/2 is a rational number, but 1/2 is not an integer. Okay, so that's showing that this is contained, and it's a proper subset and not an equal set. Last subset here, we're trying to show that the set of rational numbers is a subset of the set of real numbers. Well, every rational number is a real number. Every rational number could be written as a repeating decimal. But there's some number that's a real number that's not a rational number. So a couple of classic examples there are square root of 2 or pi. Those are real numbers, but they are not rational numbers. So that's it for this video. See you next time.